EXAFS studies of oxides and salts dispersed on surface of substance as a monolayer. Before my presentation, I would like to thank my co-workers, Dr. Cai Xiao-hai, Wang Zijie, and Professor Tang Yuqi. Dr. Cai Xiao-hai also attended this meeting. Most of the experiments and data treatment were done by Dr. Cai. Maybe some people have known that our lab has working in the spontaneous monolayer dispersion for years. In our lab, we have found many oxides and salts can disperse spontaneously. This spontaneous means thermodynamic. Spontaneously onto support of high surface area as a monolayer or submonolayer. This is a very widespread phenomenon occurs in catalyst studies. Because many real catalysts are supported oxides and salts, and most the precursors of supported metal catalysts are oxides and salts dispersed on high surface supports. And many additives and promoters in catalysts, in supported catalysts, also are oxides and salts dispersed on high surface area supports. So this phenomenon is very widespread related to many kinds of catalysts. We have confirmed this monolayer dispersion phenomenon by many techniques. But the surface structure of the monolayer dispersion is very difficult to detect because these systems are in amorphous state. It's not a single crystal. You cannot use the common techniques like lead or STM to measure the surface structure. EXAFS is not a technique only used for the surface structure determination. Actually, in general, it's used for the bulk structure determination. But we found EXAFS is also a very powerful technique for the study of surface structure of the monolayer dispersion space. Because in this system, the monolayer dispersion capacity is very high and very easy to obtain a good EXAFS spectrum. The second reason is the structure of monolayer dispersion space is very different from the crystallized state of oxide and salts. We have studied a lot of systems by EXAFS. And today I will show several examples. The first system I will show you is nickel oxide supported on alumina. The sample is prepared by very common general method, just by impregnating the gamma alumina with nickel nitrate and thermal decomposition. From these XRD patterns, we can find in the pure gamma alumina, I have no XRD. In the high loading nickel oxide on alumina, we can find the nickel oxide peak very high. In low loading, we cannot find the peak of the nickel oxide, nickel oxide. From the quantitative measurement of the peak area, we can obtain that the nickel oxide crystal phase amount in the samples. Then we can obtain we can obtain a very common bond like this. All the similar systems have this kind of bond. We can find a critical loading of a nickel oxide on alumina. If the loading exceeded this critical amount, then the crystal phase of nickel oxide increase linearly. But below this point, we cannot find the nickel oxide crystal. In this region, it's in a monolayer state. EXAFS gives very strong evidence for this one. This is the Fourier transform of EXAFS of nickel Kx for the nickel gamma ray system. We can find for the pure nickel oxide, there is a very high peak of nickel-nickel bond and a lower peak of nickel-oxygen bond. The nickel peak is much higher than nickel-oxygen because nickel oxide has a sodium chloride-like structure. The nickel in the center has the 6 neighbor of oxygen, but 12 neighbor of nickel. 6 neighbor is nickel, and 12 neighbor, 12. And so 12 nickel neighbor. And so because nickel has a stronger electron scattering ability. So the peak is and the number of coordination is high, so the peak is much higher than nickel oxygen. But for the supported monolayer, I have realized the monolayer state, the supported catalyst. The nickel peak decreases sharply as the loading of nickel oxide decreases. In this sample, the nickel oxide is below the critical amount, so one monolayer dispersion amount. The nickel almost disappears, and the nickel oxygen is almost the same as the pure nickel oxide. This result is very good, consistent with the monolayer dispersion model. Because the nickel oxide, as soon as the nickel oxide is dispersed on the surface of alumina, then the nickel still can contact oxygen ions on the surface of the alumina. But the nickel labels will become much less than in the crystal phase of nickel oxide. By using a so-called isolating phase calculation developed by Dr. Wu in Physics Institute in China, we can obtain the monolayer state coordination number of nickel in these samples. So for example, for these two samples, in this sample we have both the crystal phase of nickel oxide and monolayer state nickel oxide. By this calculation, we can separate these two phases and only obtain the nickel coordination number of the monolayer state. The calculation result is this. This is only the nickel coordination number. We can find the coordination is the function of the loading. There is a triangle here. The turning point is just the same as the turning point affected by X-ray diffraction, so-called pressure volume or critical loading. In the monolayer legend, the coefficient number of nickel-nickel is decreased sharply as the loading decreases. In the low loading, the nickel-nickel much less than 1. But in the throughout carbon and monolayer state, then they attain about 4 coordinate nickel-nickel coordination number. This number is very reasonable. For a 2-dimensional nickel has 4 nickel neighbor number. So this sound shows us that in the monolayer state, the nickel dispersed randomly by the surface. In the low loading, the nickel-nickel separated, isolated, and not come together to form a so-called island or patches. So it gives us a very clear model, a structural model of the monolayer dispersion. The second system I would like to show you is the complete bromide supported alumina. The sample is very smooth just by grinding the mixture of the complete bromide and alumina at low temperature, or by heating the mechanical mixture at 60 centigrade. We can find for a pure complete bromide, there is a very high peak of couple bond bond. But in the catalyst for the supported complete bromide, the low loading, the peak also decreases a lot. And this is a couple oxygen bond peak appears. So it's also very, because couple chlorine is first on the surface, then the couple can contain the oxygen of the alumina. So a new peak, a new bond, a new peak appears. And for this system, we can measure both not only the copper, can also measure the chlorine EXAFS. This same Fe and real transfer of the chlorine KH. Also have a very high peak of copper chlorine, and this peak decreases as loading decreases. This peak decreases very sharply. Now also, this two picture is two patterns consist very well. The third example I would like to show you is a real catalyst, a complete chloride supported alumina. This is a so-called oxychlorination catalyst. Oxychlorination catalyst. It's the ethylene. By using this catalyst, we can make ethylene chloride by ethylene and oxygen and hydrochloric acid. For a pure complete chloride, we can find a very high peak of copper chloride. For a pure copper oxygen, copper oxide, we can find copper oxygen peak here. Because copper oxygen form is solid and copper chloride bond. In the catalyst, in the supported complete chloride, we found a peak. We found a very peak. is in between these two things. Because in this system, the couple already displaced by the surface. So it forms some new couple oxygen bond, and also prevents some couple chlorine bond. But these two peaks cannot distinguish. So it has a double peak in between these two peaks. So it's also very consistent with the monolayer model. And this, by fitting the data, the coordination number, the coordination number of couple and chlorine, we found is very low at a low loading. This result is very quickly consistent with the catalytic behavior of the catalyst. For this catalyst, its couple chloride loading is very low. Not only their activity, but also their specific catalyst activity is much lower than in the higher loading. The best loading is just close to the monolayer capacity. But it's a very low loading, the specific capacity activity is very low, almost zero for the low loading sample. For example, this sample, not only activity but specific according on the couple, unit couple. This is because that in the monolayer dispersion state, if the loading is high enough or close to the monolayer coverage, then you can have two couple share one chlorine. So then we can have the couple have two chlorine label. But as the nickel oxide situation, if there is a low loading, the couple disperse randomly, then the couple may be separated in a very long distance. So in this situation, the couple Cu-Cl2, the Cl2 is not always go together with the couple. Then maybe the Cl2 go to other place of the support. So then in this situation, we cannot get activated center. Activated center with two coils. In this situation, we can have a couple with two coils. We suggest that this is the activated center. Because in the reaction need two. The mechanism suggested that mechanism I don't want to tell more too detail. But this reaction needs two coils, and this reaction has a reduction oxygen conversion. So we need two coil label. So in the low loading, we have not two coils as a label for one coil. So it's the activity is very low. The final example, I will go there. The final system I would like to show you is also a nickel catalyst. It's a nickel sulfate supported on alumina. This is the oligomerization of ethylene and propylene. For example, this is a X-ray result. X-ray result. We can also have the threshold value here, and it has a higher activity for this ethylene dimerization, higher in this component. Then in this catalyst, in the EXAFS result of this catalyst, also we can find median peak is very small, And the oxygen P is high for the catalyst. For the catalyst, the oxygen P is almost the same as the pure nickel sulfate. This is the real catalyst component. And this is almost the same for the pure nickel sulfate and 80% okay. But the nickel decreases a lot. So from all these systems, the exam result, you can come to the conclusion. Exams are studies that perform the monolayer dispersion of oxides or salts on high surface of parts. The monolayer dispersion state has a common feature. The first, metal-metal coordination number and the mm EXAFS of the oxide or salts are much lower than that of the crystallized phase. The second, new bonds will be formed between the ions of the dispersed salts and the support. Then, new EXAFS peaks, just like the CO peak in this system, we are here. For the monolayer dispersion oxides, the metal oxygen peak will be no good chance in comparison with that of the oxide crystal, for example, in these two systems. Thanks for your attention.
We have 5 minutes left for discussion.
Professor Cai Xiao-hai. I have a question about the monolayer distribution of the oxide on surface. This is a common phenomenon applied to all kinds of substrates, high surface
but for different parts, the loading is different. Sometimes the full coverage, the total coverage, sometimes 50%, 70%, 30%, or different apart.
I have a comment. We have year-long experiment on fluid oxide, well, basically without any catalyst system. We find that high temperature treatment, we also not observe any fluid oxide crystal. And our conjecture at that point is there is surface spinel form. Found that it's very susceptible to reaction. It's not really situation.
In our paper, we want you have some comment about the so-called spinel form, surface spinel form. Actually, our so-called one surface is a weak or even strong chemical surface forming. So in general, in many systems or families, the so-called surface result, we don't agree on this concept. Because spinel is a box is a three-dimensional concept. It functions by 2 dimensions spinel. So it might be in some setup, for example, in any literature, for example, from the UV setup and some other setup, they found some heat from a pure spinel. They also found some heat similar in this one situation. There is some